the screen, we are going to be looking at sequence alignment, molecular phylogenetics, RNA sequence analysis, pre-processing workflow. That is a continuation from where Dr. Saliu stopped yesterday. Then Dr. Ajayi will also come up again to take us protein tertiary structure prediction. And then lastly today, Dr. Fatoke will be taking us through molecular docking of small molecules and macromolecules. I believe it's going to be a quite exciting time. So without wasting much time, I will call on the first lecturer, Dr. Fatoke, to start the lecture now. So please, Dr. Fatoke, you have the floor, please. I will stop sharing my screen now so that you can start.
All right, good morning, sir, and good morning to all our participants and our facilitators, as well as our co-hosts over there. Today, we are going to start this training by discussing and get trained about sequence alignment and molecular phylogenetics. The two are interwoven. There is no way you want to do molecular phylogenetics that you will not talk about sequence alignment. And in bioinformatics, sequence alignment is very central because everything we want to do, we want to talk about the protein, talk about the RNA, talk about DNA, we are working from their sequence, the sequence that were generated from all the monomers, the amino acid, the nucleotide bases that were generated. So those are the things that serve as the basis for bioinformatics analysis. So once we can understand those sequences, then from there, we can predict their structure. Then from there, anything we want to do, maybe to dock or to mutate that particular structure, all those ones are possible. So this morning, we talk about sequence alignment, and then we will link it to molecular docking, molecular phylogenetics. Molecular phylogenetics, I'm trying to share my screen now. Okay. Okay, I'm coming. So I'll be brief about the introduction, then go to the answer immediately. If you talk about sequence alignment, that is, you want to align, you want to match sequence together. You have sequence A, you want to match it with sequence B. Maybe you have a sequence from a human being. Okay, then you want to match it with another sequence from a rat. That is, maybe you are using a protein, or you are using RNA, or you are using DNA. Those are the macromolecules sequence that we can have. So if you talk about alignment, you are trying to match to see areas of similarities or areas of differences. Okay, so that is the basic introduction about sequence alignment. And we have two types of sequence alignment. We have the pairwise sequence alignment, which is where you just want to match only two sequence. But another one is a multiple sequence alignment, where you want to match more than two sequence. Okay, more than two sequences. That is 2, 3, 4, 5, 3, 4, 5, 6, up to 100, up to 1,000. Okay, so that is about sequence alignment. Why is sequence alignment so very, very important? Either pairwise sequence alignment or multiple sequence alignment. It's very, very important because it helps us to identify areas of similarities and dissimilarities. Okay, and it will give us a score. In terms of alignment, we have what we call a percentage identity and also percentage similarity. I'll quickly explain that. If you talk about, let me take a protein sequence for an example now. You want to match two protein sequences together. Protein sequence A and another protein sequence B. You want to align them together. Where they match, in terms of amino acid, we have subclasses of amino acid, 20 essential amino acids. We have those ones that are polar, we have those ones that are hydrophobic, we have those ones that are positively charged, those ones that are negatively charged, and those ones that are neutral. Okay. So let's say, for example, in the protein A, you have a polar amino acid there in one particular spot. And the protein B, also you have the same polar amino acid. If it's a, let's say now glutamate, you have it in a protein A. At the same point in protein B, you have glutamate also. So that kind of matching is kind of what you call similarity. Similarity, that is, the amino acid that you can see in protein A at one particular point is what you can see in protein B at one particular point. So that is a kind of a match. We call that one similarity. But in terms of identity, let's say in protein A, you have glutamate at one particular point, but in protein B, which is at the same particular point, you are having, let's say, aspartate, which is also positively charged, what is it called, negatively charged amino acid. So we can see that, okay, this particular one that is, glutamate here, but here now you have aspartate. Yes, they are negatively charged amino acid, but they are not similar, though they can still replace each other and perform the same function in terms of bonding, formation, and the rest like that. So that kind of position is what we refer to as identity. Yes, they are not the same in terms of similarity, but they are identical in terms of operation. So they can still perform the same bonding with another set of interaction that they want to do. So that kind of interaction is identity. But in the whole sequence also, we can have area that they are not matched. When you have glutamate want to replace let's say proline. So you can see that these two amino acids, they are not matched in terms of normal similarity, in terms of identity, they are not matched. So as a result of that, the pairwise algorithm, we try to create what we call gap penalty. Okay, it will leave a space in between the two match. Okay, this one, they are not the same in any way. So it will create a kind of a gap in between. So that gap, it will give it score. The one that are similar glutamate to glutamate, it will give you a score, very high score. The one that is identical, glutamate or aspartate, okay, it will give you a lower score. While the one that are not matched at all, it will give it a 0 score and create a gap. So that is how the algorithm will align all the amino acids present in protein A and the one in a protein B. So areas that are aligned will now be summed together in terms of percentage identity and percentage similarity. And going back to pairwise alignments, the method, the algorithm that is being used for pairwise alignments, they are of two types, because we have two types of pairwise alignments. We have what we call local pairwise alignments, and we have global pairwise alignments. Local pairwise alignment and global pairwise alignment. Okay, so the difference between these two is just about where they align within the two sequences. For global sequence alignment, the algorithm is a Needleman-Wunsch algorithm. So this particular one, we take the amino acid of the first protein from number 1 to the last number and compare it with the second protein, the sequence of second protein from number 1 to the last point. So it will match all in all of protein A, match it against all of protein B, and we try to give a score for it. So that is about this particular algorithm, Needleman-Wunsch algorithm. It's a global alignment pairwise algorithm. But let me just go down, okay. But for the local sequence alignment, local pairwise sequence alignment, this particular algorithm, which is called Smith-Waterman algorithm, Smith-Waterman algorithm, this particular one, we try to look at the protein A and find area that is conserved, and try to match it against protein B in an area that is conserved in protein B. So it will not start from the beginning, from the first amino acid and the end amino acid compared with the other one, just like Needleman-Wunsch. So this one will look for areas that are conserved between the two proteins, and that is where it will do the alignment. That's where you do the alignment. And also we have another one which we're still going to use. We call it a blast. All of us, majority of us, we are familiar with that particular time. So this particular one is an example of a Smith-Waterman algorithm, but it makes use of what we call a heuristic. So that particular one, we try to define a machine. And this blast is used in maybe when you are considering larger database. So you can consider more than two sequence. Okay, one sequence against another sequence in a database. So you can compare just initial sequence against thousands of other sequence and give you their percentage identity and the percentage similarity as the result. That is about pairwise alignment. Pairwise alignment. Okay, I've talked about. So the significance of pairwise alignment is that it is very useful to compare biological sequence, and that's application in molecular biology. Yes, I will still make mention of it by the time I'm talking about sequence alignment. Maybe you want to design a primer, you have to look for the conserved area in your protein A, in your enzyme A, and compare it with the one that's other organism that you want to use as a template. Then in evolutionary biology, they make use of it also because it makes us to infer how two proteins are similar in the course of evolution. Let me quickly go to multiple sequence alignment. Multiple sequence alignment is one of the central valuable tools in bioinformatics because it has wider application than pairwise alignment. Number one, let's say you want to do homology identification. That is, you want to compare conserved region across multiple proteins. Maybe they belong to the same family or close family. Multiple sequence alignment can help us even to identify that. We want to identify a domain, we want to identify a motif. So multiple sequence alignments will help us to identify that. And multiple sequence alignments serve as basis for phylogenetic analysis. Phylogenetic analysis, okay, you want to consider how evolutionary history of a different organism, 10 organism, 15 organism, 20 organism, 30 organism, using the same set of enzyme or the same set of a gene. Yes, you can use the DNA sequence or protein sequence to do this analysis. So phylogenetic analysis built upon multiple sequence alignment. Then if you want to predict protein structure prediction, is still possible when you start from the homology sequence. By the time our lecturer, our facilitator, Mrs. Ajayi will be talking about that. So we see how homology, multiple sequence alignments comes in determining the protein structure. They have to do the matching underground before they will now construct the structure for us. Yeah, I have said conservation, the conserved motif or domain identification. We can use multiple sequence alignment to do that. Then structural alignment, primer design. I've made mention of that. When you want to design a primer to conduct your PCR, then you need to do multiple sequence alignment to understand the conserved area that, okay, this area is specific to this particular organism or this particular family of a species. Okay, so by doing multiple sequence alignment, you understand the area where that can serve as your primer on which a DNA polymerase will be able to amplify. Then in vaccine development, multiple sequence alignment is very, very, very important in the development of a vaccine. You have to look for the epitope even on that particular pathogen area that is causing the problem on the protein. Specifically, if you take COVID, for example, we have a different kind of protein in COVID, yes, in SARS. So we can say, okay, we have spike glycoprotein. So what they just need to do, okay, they will take the sequence of spike glycoprotein and then align it with other kind of a glycoprotein in other organism and the rest like that. And then they will try to find, okay, in this particular spike glycoprotein, which area of this protein that's really causing the problem. Okay, once they can identify the segment that is really causing the problem, then they can what? They can try to mutate that particular segment and synthesize it, or they can clone it, and then from there they will now use it to test. So they don't need all the exact protein to develop a vaccine. So you just need the epitope, that is the region of antigen that is causing the problem. So that is about the vaccine development. And we have different types of vaccine, as you know. We have the one that are RNA based, we have the one that are synthetic based, and we have the one that make use of a dead virus or dead or pathogen for development of protein or a vaccine. So multiple sequence is very, very important. Then coming to molecular phylogenetics. Molecular phylogenetics is different from the one of biology that make use of the whole organism. If you talk about molecular, we are talking about something within the cell, okay? Not physiological phylogenetics now, okay? It's not the one that archaeologists make use of, but this particular, we are talking something that's going on within the cell, molecules within the cell. You are using it to characterize the evolutionary trend of that particular organism. So this particular one can only give us a scope about segments of that organism. So we cannot use it to actually conclude that this organism is totally similar to another organism, except we do the actual all the proteins or all the genes that are present in one organism. We try to experiment it against another set of organisms. But if you are focusing on an enzyme or a particular gene, then our analysis, our reports will be based on that particular gene. So we don't infer what is beyond our experiments, what's beyond our experiments. So this one, we can make use of DNA sequence or protein sequence also. So in molecular biology, genetics, so they use it to infer the evolution of a particular set of enzyme, okay, in one particular organism against another species of organism. And the steps, we by the time we are doing the hands-on, we see the steps. It's very straightforward. So once we generate the tree, then we can now classify one organism gene or enzyme against another organism gene or enzyme. So we have two types of evolutionary trend. Two types of evolutionary trend. We have a paralog and the autolog. Paralog and autolog. Okay, so autolog, when you have maybe the same gene present in an organism and performing different function, and paralog, when you have this, the same gene in different organism but doing different function. So you can just go about those two terms, paralog and autolog. Paralog and autolog. So one occurs as a gene duplication, that one should be autolog, while another one occurs as a result of a speciation, when species is being diverged. They were told us that we diverge from a chimpanzee. Okay, so during the speciation, maybe our gene, one gene or the other, is being differ from the one of from a chimpanzee. But the one of gene duplication in human being itself, you have a particular gene, two genes that are present in human being, but they are performing different function. So that is about autolog, while paralog is about the speciation. Okay, and by using molecular phylogenetics, we can determine how this particular gene or this particular enzyme has diverged over the trend of evolution. So we can predict, okay, this particular gene has diverged over set of evolutionary time. So now we want to go to the hands-on. That is just a short introduction to the topic. So as you can see on my screen here, hands-on. Okay, as you can see on my screen here, hands-on. For this training, we will use a protein sequence of a human mannosidase. Mannosidase is an enzyme that catalyzes mannose sugar. Okay, so we use that. So I want you to open your computer now and connect to the internet, and let's do some analysis here. So I will give you just a minute to do that if you have not done so. Open your laptop, open your tablet, and let's work on sequence alignment. So immediately you open your laptop and you connect to the internet, we have to go to protein sequence database to get our sequence. Protein sequence database to get our sequence. We have protein structure database also, PDB, okay? So we have protein structure database. Since we are working on sequence, So on the central port where you can get sequence is this particular uniprot.org, www.uniprot.org. So immediately you open your computer, connect to the internet access, then type this www.uniprot.org. And then we are going to search, either we use the manosidase and click the one of woman, or just directly we type this particular code. So let me copy the code now. Let me copy the code. Okay, just copy the code. So immediately you visit this particular site, www.uniprot.org. Let me click on it. Okay. Okay, this is how the interface of Uniprot look like. Okay. So we have where a search box and we have other things over there. But since we want to use the Uniprot ID, so you don't need to paste the code, your Uniprot code, just paste it. Just paste into the search box. Okay, let me go.
462.
Yes. So that is
Please,
it.
the code.
O.
Okay, 00046.
No, the first one is O. Then the other one is 00462. Is there on the screen now? O 00462.
Okay, 00046.
It's not 000, it's O, then 00462. O for the alphabet.
Please, we are going to go to that Uniprot something. Then we now type the something, the
in the
code.
search box. Yes.
Right. Okay.
Yes.
That search box. Okay. Yes. Okay.
So once we search it, we bring out this particular interface for us.
Okay. All right. Yeah, please continue. Our teacher, carry others along. Others, please, if you are having issues, you can just indicate. But don't slow us down unnecessarily, but we just want you to catch up. We don't want anybody to be lagging behind. Thank you.
Okay. So let me quickly check what is in the chat box. Okay, there's nothing there. Okay. Let me go back to the. So this is on the Uniprot interface now. Okay. So based on that particular information, we need to go to the sequence section. So that's where we get our sequence. We see a kind of table of content on the left-hand side. So just scroll to the one of a sequence. Go to the one of sequence and click on the sequence. So immediately it will jump to where we have the sequence on that particular interface. So this is the sequence for that beta minosidase of human being. Okay, beta minosidase of human being. So what's based on what you need to do is to copy this particular sequence. Open your MS Word, fresh page of MS Word. So we try to copy this particular sequence. And how to copy is this. Just click on a copy sequence. Copy sequence. You can see it on the interface. Okay, copy sequence. So once you copy like that, or better still, let me check on the faster. Okay, I think copy sequence will do that for us. So once you copy the sequence, then you can go and paste it on the MS Word. So all the information that we need about this particular protein will be there. It should be in a faster format. Faster format always start with a greater than sign. So you see the greater than sign. once you paste this particular sequence, it'll be in that particular format. Let me see download. Okay, or better still, you can first click on download. So once you click on download there, you can now copy all the sequence that you can see on your interface. Let me go back a bit. Okay, UniProt. So from the UniProt, just need to search for that particular code. Click search. So click on table format. Okay, scroll to the sequence tab. So once you go to the sequence tab, just click on download. So once you click on download, it will bring another interface for you where you can easily copy all the sequence that you can see on my interface. Just copy everything, starting with that greater than sign, and paste it in a fresh Microsoft Word page. So just paste it there. So that is our sequence for this monocytes of human being. So just copy it there. Then we still need to go back to the same page under the sequence. So this particular, I have to go back. I have to start again from, let me see if this one will work. Okay, all right. So we have to go back to the sequence. Once we have copied that, go back to the sequence. Under the sequence, you will see what we have, tools. Tools, you can see it on my screen, tools. That is under the sequence section, tools. Okay, so just open the tools, open it, you will see sub options. Okay, so this option, you can use it depending on the analysis that you want to do. If you want to compute the isolatory point or molecular weight for this particular protein sequence, just click on compute PI. PI means isolatory point, or if you want to compute the molecular scale. Then if you want to determine maybe other parameters of this particular protein, just click on plot param. Then if you want to cut this particular sequence, maybe you want to mimic a digestive enzyme, okay, just click on a peptide cutter. It will bring option for you, okay, which enzyme you want to use to cut, which protease, which digestive enzyme. Is it trypsin, chymotrypsin that you want to use to cut this particular protein sequence? So by that, you can get the fragment of peptide that you can use for your further analysis. But this time, I what want to use is a blast. Okay, so click on the tools, click on blast. Okay, so it will bring another interface for you like this. Anything again. So this is scroll down. Don't need to change anything here. If you want to title your work, you can title it over there. You can title it over there. Oh, this one is back. Okay, you can title it over there. Then look at this advanced parameter section. Advanced parameter section. Okay, since we are using protein sequence, that is why we have this one as protein. If you are using DNA or RNA sequence, you will click on DNA or RNA. Okay, then the type of program, we have different variants of a blast. Okay, we have blast N, we have blast X, we have T blast X. We have about 7 different type of blasts which have their own meaning. Okay, which have their own meaning. But blast P is where you are using protein sequence to query protein database. You are using protein sequence to query protein database. Okay, so blast N, I think when you are using nucleotide sequence to query the nucleotide database. Then we have T blast X, that is, you want to convert protein sequence, you want to use it to query nucleotide database, then get the nucleotide results of that particular protein. So that's a bit, since we are interested in protein against protein, that's why we are using blast P. There we have the threshold, which are default, which by the time you are familiar with this, you can change one or two things about this parameter, but we will leave it the way it is since we are using BLAST-P. So what you just need to click is click on Run Blast. Run Blast. You can see it under here. So just click on Run Blast. It will load. It will load. Just within 1 or 2 minutes, we get our results. So we get our results. So once the results show now, what we want to do is that we want to see another 7 organisms that have high similarity or identity with this our human sequence. So we try to copy the best 7 organisms that has high similarities with this our human protein sequence. So once we copy that, we copy each of the sequence of this other organism and we paste it under the MS Word that we have created. So we post it under the initial sequence that we have pasted in that MS Word. So in all, we will have 8 sequences that we now use for our multiple sequence alignment. So once the result of this particular one is done, we try to copy 7 organisms that have a high percentage similarity with this human monocidase. So we copy their sequence out. Each of these organisms, we copy it out and paste it in our MS Word. Then immediately from there, we can now conduct our pairwise alignment and multiple sequence alignment to see how it works. So this particular one is still running. So we'll notify you when the result is ready. Okay, is it true that I click? I think it's supposed to be 1044, 1043. Let me delete this other one. So only one should be running. Okay, so your own also will be running like that.
Still running?
Yes, it's still running. You try to match that our human monocidase. Try to match it against the protein sequence database. Protein sequence to see those ones that match. Okay, so my own interface, I have to go back so that I will start. Okay, let me still wait a bit to see if it will within 1 or 2 minutes.
Please, let's wait till it finishes.
Okay.
Running.
All right. All right.
Mine is completed.
Okay, good. Okay. So, okay, once you have
Please,
your own.
let's wait for that.
Okay.
Mine is completed.
Good. Okay. Let's just wait for more people. So I will just explain what we need to do, then
mine too is completed.
Good. Okay, just look at the result while we are still waiting for others on my own. You will see in front of the list, the list will be so enormous, maybe like 250 on that particular list. The first one that you have there will be our own protein, human monocidase, and the identity will be like maybe 100%. 100%. Then after that, you start to see different protein from different organisms that are not.
Please come again.
Okay, on the result page.
Our lecturer, please.
Okay, sir.
The thing is completed, right?
Yes.
So let's take it from there, please.
Okay. On the results, that the completed results, we should have a list of different proteins on that interface.
That's true. I can see Homo sapiens, gorilla.
Okay, good. Okay, good. So if you go towards the right-hand side, you will see percentage identity. Can you see that on some headings? And then they will write 100% somewhere, some maybe 99%.
Yes, I can see that.
Okay. Then there are another what is it called now? We have a Z-score, we have byte, we have p-value. Is there anything like p over there?
I'm sorry. Let me just tell you what I see here.
Okay.
Here in my own, it told me 2 results: blast, status completed, created, 23,530, name. So it just brought out one link, NCBI blast, whatever, T1M. That's what I
You
saw.
click on it. You click on it. Click on it.
Okay, I will click on that link that it brought. Okay, that under blast, I will click on that.
Yes,
okay.
yes.
All right, thank you. I've clicked on it.
All right, sir.
Okay, I can see all the information now. Thank you.
Okay, so mine is still running. I don't know, maybe it's my network or the platform that I'm using. Okay, so what you need to do now is this. Okay, on that particular interface, we have different set of organisms that has similarity with that our protein. Our protein, which is a human monocyte, will be the first one there, and the identity will be around 100%, exactly 100%, because it's still the same thing. Then another, maybe by the time you go towards the right, we see some parameters on top, like p value, e, which is the expectation level. Then we have z byte or z score now. Okay, so just look at under that particular percentage identity. You will see different organisms that has close similarity or identity with our protein, maybe 99%, 97%. The thing will be reducing like that. Will be reducing like that.
Yes,
Can we see that?
Yes, that of gorilla. Gorilla is 99.4.
Okay. Then if you scroll down, any other organism? So we just want to select 7 organisms from that particular list to work with. Their percentage identity will be different. The percentage identity will be different, will not be the same. Okay, can we do that? So just try and click on the first organism. Once you click on the name, then it will take you to where you will see the sequence.
Our teacher, please. I've seen the blast results.
Okay.
I've seen the blast parameters identity. The first one there, 67.6 and 100. But
Okay,
it was
okay.
mentioning gorilla. I don't know where it's all.
Okay, my own is complete. Now let me click on it so that we follow together.
Better.
Okay.
Better.
Lecturer, sir.
Yeah.
Thank you. Please try as much as possible to follow. I know it might not be easy. Try as much as possible to follow through with the chat. Some people are saying that you are too fast.
Okay.
Yeah, some people are saying that if you be coming down, that you are too fast.
All right.
And then somebody's saying that somebody said their own. I think maybe the rate at which their system work is not as fast as yours. So in terms of
even my own is slower now because
yeah,
I'm
in
using...
terms of instruction, try to slow down, sir, so that we can carry as many people as possible along.
All right, sir. All right, sir.
So
okay,
you have
so
a question. You have a question.
Your
Yes,
own
sir.
is on now, so we can see your own.
Yes, my own is on. So let's just follow my step by step. Okay.
All right.
So this particular first one is our own. You can see the code 00462. That is our the one that we submitted for the analysis. And you see on this extreme left is 100% identity. 100% identity. Then follow, if you look at the organism, the next one to it is gorilla. You see the same beta manus,
Yes,
gorilla.
yes.
Then followed by paniscus, which is a chimpanzee.
Yes.
That one is also 94%. Then we have another type of a chimpanzee. We just pick one of the chimpanzee. Then we have, different kind of organism over there. Monkey, can see monkey now, Rhinopithecus, and the rest. So that one is 97%. So the percentage we start reducing how they are close to our initial sequence. Then here we have pig, macaca, manesti, and the rest like that. So what we want to do is we want to pick 7 different sequences from different organisms. So let's pick, so let's pick the one of a gorilla. So what you just need to do is either we click on the name here for that particular gorilla. I think if you are working on the laptop, everything will be, the screen will be full. So just click on the name, can right click. Once you right click, open in another interface. So it take you to that UniProt entry, and then you go to under the sequence, then you copy the sequence the way we did for the initial one that we were working with. So we click the one for the gorilla. Okay. Let's click the one that follow this paniscus. What just to do is to right click on this particular entry name, which one I'm highlighted now. Once you right click on it, open it in another tab, then go to under the sequence and copy the sequence out the way we have done for the first one. Click on download, it will open, then copy all the sequence, paste it under the Microsoft Word where we are pasting our sequence. Then once we click the one of panis, this, can just click any other, just make it 7. Just want to see how the alignment will go. So you can click on any of these amino acid organism. So anyone that you are interested in, you can scroll down, pick anyone. Just but must ensure that we click at least 7. At least 7, so that by the time we want to run multiple sequence alignments, we'll be able to see the beauty. So just click on the entry name, right click on it, open in another interface, scroll down to the sequence section. On the sequence section, click on download, then copy the sequence. Copy the sequence, everything that show on that particular download interface. Copy it, then paste it in that MS Word page.
Teacher, please.
All right, sir.
Some people are finding it difficult to copy. Exactly what are you clicking? Are you clicking the name? For example,
In order to retain, yes, sir. In order to retain this particular page, that's why I said they should right click. We are clicking on the entry name. Entry name, that is the first thing on the column.
That is
so
0.
Entry name for,
is it the 0046?
Yes, we are not clicking on that first one because that is our query
organism.
So any other one we want to use, okay, just right click on it, then open another interface.
Okay.
Then once you right click on it and open another interface,
okay,
it will bring you to that normal interface that we were before. Then on the left hand side, you still see sequence. On the tab on the left hand side, you see sequence. Let me just open this other one now. Okay, let's say I click on this other one, the GR2R2. So it will bring me to this kind of interface, just like the one we have before. So on this left side, which one I'm trying to move up and down? The one I'm trying to move up and down, just move to under sequence and click on the sequence. It's a kind of a tab. So if we jump to where we have sequence on that particular page, it will jump to where we have sequence on that particular page. Then once we reach there, just click on this download button, download, the way we did for our manus. Just click on download. So So once you click on download, it will bring this interface for us. So all the information about this protein, that is what we can see in that first line. Beta manus, organism, we have gorilla, then all the other informations over there. So you just need to copy, highlight all this O sequence, highlight everything, and copy it. So once you copy, go and paste in that MS Word that you have opened already. Okay. So once you have copied this one, you paste it into that MS Word. Just leave a kind of a space between the first one that we have pasted, then copy this one. So the same thing, just try to get additional 7 sequence from that particular list. So just try to open additional 7 to make it. You can try to look for different organisms so that it will not be gorilla. You can try to look for pig, try to look for maybe cats, or that particular. Let me go back to that particular list. So that is how to copy each of the sequence. We just copy it out one after another. Okay, let me go back once more. Okay, this is still our list. Okay, so we have done with that G3R2R2. So you can just look again. Okay, we want to copy another organism. Okay, chimpanzee, which is the next one. So you just to click on this A0, A2, R9, A4, something. Just click on it. Follow the same process. Click on sequence. Click on download. Copy the sequence. So then we look for another one. So you can just do this one randomly. Just pick the one that's any organism. You can pick the first 7. If you pick the first 7, I think majority is chimpanzee. But we want something that will help us to see the beauty of this alignment. So you can choose another organism. Okay, you can choose this other one, the gibbon. So what you're just to do is to click on the entry name, scroll down to the sequence, click on it, then click on download, then copy the sequence and paste it into your MS Word. Then scroll down again, try to look for another organism, monkey. Okay, you click, want to pick that one of monkey, click on the entry name. Once you click on the entry name, A0A2K6PY6, then scroll to under the sequence, click on it. On the sequence section, click on download, then copy the sequence and paste into your MS Word. So as many that you are interested in, then we can copy the sequence out. Okay, so that is how to do that. So you just copy the one that you are interested in, and then you go ahead. So let me just wait till we have at least 8 sequence in our MS Word. So once we are done with that, let me know. So just copy at least additional 7 from this page, apart from the UMA manus that we use as our initial query protein sequence. So just try to copy additional 7 from here. So you can scroll down, and you know that as we are scrolling down, the identity percentage is reducing. As we are scrolling down, the identity is reducing 95, 95, 96, still like that. Then some could be 98, 89, 89. You scroll down, we have 84, 80, 80, you have like 40 and the rest like that. So here we have a 69, 69, and so forth, and so forth. So this is this one will help us if you have maybe the set of organism in targets. So what you just need to do is to look at this particular list, scroll to where you can get all those organisms, and then you pick the organism that you are interested in, that you want to do your comparison with. Maybe you want to compare human being against rats. So you just try to look for rats in this place. Maybe you want to compare with fish, look for anyone that is fish over here, okay, based on your research focus. Okay, maybe you want to compare protein human being against the one in amphibian. Then you look for organisms that are amphibian from this particular list. Then you copy their sequence out. Then from there now we can now do our pairwise alignments and multiple sequence alignment, then construct our phylogenetic tree. So if you are done with 7 sequence, if you are copying 7 sequence, just let me know. So we can work with 5, but at least I want you to at least have a good number that you can easily check. If you are true, just let me know so that we can move to the next step.
I'm true. But others
Alright,
are
sir.
still working. Yeah.
Let's give them like a minute or so. Just copy, do 7 more sequence with the one that we have initial as a woman monocidase.
I'm true.
Okay, let's wait for 2 more people.
How many space are we supposed to leave in between each sequence?
Just one is okay. One is okay. If you put 2, it doesn't matter. By the time we want to use it, we still copy the one we want to use. It's only a multiple sequence alignment that will copy everything. But for pairwise alignment, we just copy the 2 that we are interested in to want to match. For pairwise, pair, that means 2. But multiple, that means more than 2. By the time we want to do pairwise alignment, we just copy 2 of those sequences. We try to match them.
So at the moment we've copied about 8, 7.
Yes.
To the
Yes. Your initial organism is human. Then we have additional 7 sequence from different kind of organism. So making 8. So you're supposed to have 8 set of sequence in that your MS Word. Okay.
Our teacher, please. Somebody
Yes.
here, Olaiton Faith. He said, my own search brought out only 1 organism. What did I input? I think maybe she's still at another level or whatever. Maybe she can speak up so that she could be assisted.
Okay.
Can you speak up? What was the problem?
It's like it's just taking me back to what I imputed. So I don't know what I missed.
At what level are you exactly?
The level I am is for me to run that inside to bring out all those 8 organisms or whatever, so I can copy. But I'm just in 1, so I can't copy anything. I don't know what I did from the back.
Okay, I think maybe you ask, do you see a kind of link like that? Maybe you have to click on that link. That is what will bring out the 8 something that you are supposed to now copy. I think you are still a bit far behind.
Yes, I'm following as he was doing it, but that is just where I am now.
I got stuck at that place the other time, and somebody told me I have to click that. That if you find the kind of link, maybe that just one, click on that blue something there. Our teacher, maybe you can assist. I don't know. Maybe I don't know.
Okay. You have searched for that human monocidase 000462.
Yes, I have it. I have the sequence already.
You have the sequence. Okay. On the Uniprot page where you copied that particular sequence, you have to go back to that same page. So once you go back to that same page, you have to move back from where you copied the sequence. Just press back arrow to take you back to the main page. Okay. So on that sequence section, you click on Tools. So on Tool, you click on Blast.
Okay, sir.
On Tool, you click on Blast.
Okay, sir.
So once you click on BLAST, it takes you to another page where it will show you your sequence again. Then show you the parameters. Okay, BLAST P. Are you on that particular page? Okay. Once on that particular page, don't tamper with the parameter. Just leave the parameter as default. Then click on Run BLAST.
Oh, thank you, sir.
So once you click on Run BLAST, it will take maybe 2 minutes, a minute, depending on the capacity of
Yes, I
the.
followed from there. Yes, sir.
Okay. So once the result is, when you obtain the result, you have at a link that show you, okay, this is the completed result. Just click on that link.
Okay.
So once you click on that link there, you should have on that interface, you have at least 250 set of proteins. So once you have that 250 set of proteins, then you can now select 7 different organisms apart from human.
Yes,
Just click on there.
all those ones. Thank you, sir.
Okay, so you are on track now. So out of those 250, just click on the entry name of 7 other organisms apart from human being. Click on the entry name. It will take you back to a kind of previous page where you have sequence. So click on the sequence, click on download, copy the sequence of that other organism, then paste it in your MS Word. Then go back to the same page of 250 list, look for another organism, click on the entry name. It will take you to where you click on the sequence. Then on the sequence, click on download, copy the sequence and paste it in your MS Word. So you do that, you have additional 5 or 6, 7 organisms in addition to human being. So you should have 8 different sequences on your MS Word. So from there now, we can now proceed to pick out of those sequences, do our pairwise sequence alignments, multiple sequence alignments, then we construct our phylogenetics tree.
Thank you, sir.
All right. So since a lot of us are done, so let me go back to the next step. So let me go back to my notes. Okay. Yeah, so we have copied the FASTA, click on into fresh MS Word, click on choose, then click on BLAST. Then this BLAST has the default, okay. Then copy the 7 sequences that have at least 70% similarity with good this and this, and paste it in MS for that use, okay. So the next thing we want to do now is we want to conduct pairwise sequence alignments. So we will conduct one for local alignments, then another one for global alignments. Local alignment make use of Smith-Waterman's method. Pairwise alignment make use of Needleman-Wunsch method. Okay, so the tools that we want to use is still online too. We are going to visit this particular site, www.ebi.ac.uk/tools/PSA. So that is a European Bioinformatics Institute in United Kingdom. So they have good tools for bioinformatics analysis, online servers for bioinformatics analysis. So we visit this particular site, www.ebi.ac/tools/PSA. So over there, we see different tools. So we click the one that belongs to local alignment, which is a Smith-Waterman's method. Then after we've done that, we go back and click the one that deal with global alignment, which is a Smith-Needleman-Wunsch method. Okay, so they call all these pairwise alignment, they call it EMBOSS, EMBOSS. So we visit the site now, and then you will copy 2 sequences from your list in MS Word. Then we use it for analysis to see the local alignment, then the global alignment, how they are similar, how they are different. So I will click on the ebi.ac.uk/choose/PSA now. Okay, you can see the title pairwise sequence alignments. Then if you just scroll down, say, do you want to compare multiple sequence? We're not doing multiple sequence at this particular step. Okay. The next thing you see over here is global alignment. So global alignment to create end-to-end, that is all in all, alignment of the sequences, alignment of the sequences. So we have different one here, but the one of a Needleman, that is what we want to use. Emboss Needleman create optimal global alignment of two sequences using the Needleman-Wunsch algorithm. Algorithm. Okay, so that's what we want to use for global alignment. If you scroll down, if you talk about local alignment to find one or more alignment describing the most similar regions within the sequence to be aligned. Okay, it could either be protein or nucleotide sequence. Okay, so we are going to use the first one, which is Emboss Smith-Waterman's algorithm to calculate local alignment of two sequences. Also, you can use this other one, it's still also local alignment, Emboss matcher. It identify local similarity between two sequences using rigorous algorithm based on L-align application. So this one is not based on Smith-Waterman's algorithm. So that is another application, L-align. It's also good tools. Okay, so but we are going to limit ourselves to the one of water emboss for local alignments, then Needleman emboss for global alignments. So let's start with the one of global alignments. So what you just need to do, click on launch. In front of that launch, you see needle. So just click on that needle. You just click on that needle. So it takes you to this particular place, emboss needle, which is a Needleman-Wunsch method. Okay. So here on the interface, it tells you, okay, what pair sequence do you want to use? If it is protein with a DNA, you can change it over here, anyone you want to use. So since we are using protein sequence, so we still click on protein. Then in this particular box, it said paste first protein sequence. Paste first protein sequence. Okay, paste first protein sequence. Paste first protein sequence. So go back to your MS Word now, copy the first protein sequence. You copy everything about your first protein sequence, which is the one of a woman monocidase. Copy that. Okay. Then go to the last sequence that you copy on that is in your MS. Paste that particular one, paste it here. The one of a woman being the sequence. The first sequence on that your MS Word. Copy everything from that greater than sign to the last amino acid sequence. Copy that and paste it in this first box. And paste it in this first box. Okay. Then he said, enter or paste your second protein in any format supported. We are using FASTA format. So go to that your list again. So this one it doesn't necessarily to be the same since we are learning. So pick another protein from your list. Pick another protein from your list. Copy everything for that particular second protein from that greater than sign to the last amino acid sequence. Just copy it and come and paste it into this second box, which is for your second protein sequence. Okay, so the option, just leave it here. The output here, let me see what sample we have in the output. Okay, just leave it at pair. We are not doing all this matrix and the rest like that. Okay, just leave it as pair. It will align the sequence for you. Then you're able to see area where they were similar or dissimilar. So once we are done that, it will not take long, so you don't need to notify by email. So within a minute or two, everything will be done. So once you have done that, you paste the first sequence into the first box, which is your human monocidase sequence. Then in the second box, paste another sequence of your interest. But take note of that particular sequence because we use it in local alignment. So paste that second sequence of your choice, paste it into this second box. So once you paste it here, then we want to compare, we want to do the pairwise alignments now. So just leave it at default option. By the time you are used to it, you can change parameter based on your interest. So don't need to be notified by email. So once you have done that, just click submit. Just click submit. Let me try to see if I can do mine. Okay. Let me go back a bit. Are we done?
Yes, I'm done.
Okay.
Yes,
So I just
I was able to see some results.
okay.
That of I use that of human and gorilla.
Okay.
So I can see alignment by ash, then different comparison between human and the gorilla.
Okay. Actually, so that I will not waste much of our time. So what this one will try to show, okay, it will match the sequence of amino acid of a human protein sequence. It will match it all in all from beginning to the end. It will match it against the one of a gorilla that you have selected. And along the way, it will show the area of match, and it will try to create a gap, or you say you have a hash there. Okay, so those are the areas they are not matched. Okay, so the area where they are matched, we see one amino acid on top, you will see another amino acid below.
Yes.
Okay,
Yeah.
then it will
Please
give you.
wait for us. So,
All right, sir.
okay, all right. Go ahead. I think you're answering a question. Go ahead, please.
Okay. It's still just about the results, so that we can move to the next one. So what this particular result will tell us that is we try to match the human monocidase sequence from beginning to the end and match it against the one that you have used. If you use the one of gorilla, it will try to match it from beginning to the end. Then it will now show us the area of similarity, and then the area where there are differences. It's either put a dash or hash. Okay, so where we have similarities, those are the area you have one amino acid on top and you have another amino acid below. Those are the areas of similarities or identity. Then it will give you a score. You should have a score of the whole global alignment score. So what is your score?
Okay. Is it at the bottom? Okay. At the bottom. Okay. Similarity. I have 99 points. Okay, 99.9 for similarity. The identity, 99.4.
Okay.
Actually, we have used something not so close to human, because gorillas are quite close to human.
Yes, but you see, if you are interested in the area that no, so you just have to just scroll over the sequence and look for amino acid where those differences occur. So now you have two results. One for similarity, which is about 99.7. The one for identity, which is 99.4. So difference of 0.3 between similarity and identity. But I've explained the reason why similarity and the identity, they are not the same. Okay. Similarity, okay, let me correct myself. Similarity, whether you have glutamate or amino aspartate, that's about similar. But identity is the one that you have glutamate. So possibility that identity will be lower than similarity is constant. Because identity is that you have the amino acid you have in A is the same amino acid you have in B. But similarity is that, okay, you have amino acid you have in A, the close family that can still perform the same function without causing any problem. That is what you have in B. So it will give you another set of score. So similarity, identity. So those are the two terms that are very essential. So similarity, they are the same up and down. Identity, they are this and this. So that is about that. So global alignment, we just try to align everything from beginning to the end. So you can still see area of similarity, where similarity. So that's about global alignments. But if you want, let's go back now and use the same set of protein. You can create another interface for this other analysis.
Hello, please.
Yes, sir.
Sorry for bringing you back.
All right, sir.
So, are there people who have not gotten to where we are, please? Maybe you are having issues. You are still behind. Anybody? All right, I think we're on the same page. So what I want you to do now is that most of us are on we have gotten the identity, similarity, and score.
Okay.
So, and then we even have details there showing the particular, is it proteins, all those MR,
Amino acid.
Those amino acids now. So where you have the same amino acid in the two sequence, that is a identity, right?
That should be similarity,
You have
identity.
RL, all those ones. Oh, Abi, what is, I don't.
Yes, similarity, similar, identical. Those two that needs to be, they are two talents.
What those two sequences are, I really want to know where you have all those 50, 50, 100, 100, 150, 150. Underneath, do we need that? Yes,
No,
I see the top. We have all the results at the top, but underneath that, what is the usefulness of those things we have under there?
Actually, what we are interested in is area where they match or where there is substitution. So area where they match, okay, you know that they match here. But area where there are substitution, so that is the area where interest should be, because you want to know what really happened that caused that particular substitution. So what really happened that caused that particular substitution? Okay. And for that substitution to occur, that means there is an evolutionary impact. But the extent of the impact, we cannot determine using this method now. By the time we want to use a multiple sequence alignment, you can now see how those small differences as make the evolutionary trend to diverge, to divert from one organism to another on this particular enzyme that we are working with. And if that particular substitution, maybe by the time we are doing structural study, okay, the next facilitator, we'll be able to, if this particular substitution occur at the active site, then it will have impacts. Okay, is it that, okay, this particular enzyme will not be able to perform excellently the same way that the one of human being? Okay, so all those things will have impact.
I get it.
All right, sir.
Thank you.
Okay, all right, sir. So that's similarity and identity. They are two common terms. If I may ask, which one has the highest score? Is it similarity or identity?
Similarity.
Similarity has the highest. Okay, so similarities make use of, okay, so identity should be the where you have G glutamate on top, glutamate below. But similarity, you try to capture, okay, you have glutamate on top, but you still have aspartate that they belongs to the same classification of amino acid, hydrophobic, or polar. You try to capture that, okay, they can still substitute each other and still perform excellent function without having great impact. But in case now having polar substituting with the hydrophobic, then it will give it a kind of a dash that they are not matched. Their function is not matched. So it will give you a dash or hash at that particular point. So that is about similarity and then. So if you try, there's a formula to calculate that. I put a kind of a resources here. So all the formula to calculate the similarities and the identity, we find it in these resources. So we don't go back to the theory. So you try to find, okay, how many amino acids is are similar. Then you try to base it all over the total number of amino acids, then multiply by 100%. So that's why we have those percentage similarity. Then try to look for number of amino acids that are identical. Then try to base it all over the total number of the amino acid present in that protein, then multiply by 100%. Then we get percentage identity. So that is about P hours. So if you go back to that, okay, that's EBI, and we click on Waterman emboss to see the local alignment. If you still use the same thing, we can now see the difference between local and global. Let's say use the same protein that we use for global. Just click on the, let's scroll down to, okay, local Waterman. Okay, just beside the launch, we see water. See water. Okay, if I click on that water, it will bring similar interface like that one of global alignment, the same protein. So try to do the same thing here. Paste in the first box here, paste the human mannose, the protein sequence of human mannose, paste it here. Then for that second protein, paste the same thing here. The second protein that you use for the global alignment the other time, paste the same set of protein here. Then we click submit. Okay, and we click submit. So just the same step, but different algorithm, and to give us different results. So let's quickly do that and see how the results will look like. So the result of this one, we try to focus on those areas where the two protein sequence are similar. Where the two protein sequence are similar, it will not compare end to end. It will not start from number one and the last number. No, it will just try to see area between the two sequence that are similar. So it will now do the calculation using that particular area, and it will still give us the percentage identity, similarity, and the other scores. So let's quickly do that and see the results. So just as I've said under the introduction, local alignment is very good when you are looking for the conserved area between the two. You are just looking for the conserved area. You are not interested in any other function. But for global alignment, you want to see everything from beginning to the end, where the differences really occur. Maybe in terms of mutational effect and the rest like that. So let's quickly do that within a minute and see the score before we go to multiple sequence alignment, which is our last. So once you get your result, just let me know so that I can follow up.
I'm done, sir.
Okay, a lot of people are saying they got the same result over here. Yes, because based on maybe the second protein that you are working with, they have almost similar to human being. Let's say you are using something very far from human being, then you'll be able to see those differences. You'll be able to see those differences. Okay, somebody said there is an increase in similarity. Okay, good. So if you look at the results, that is Olubum Ebenezer. Okay, if you look at the result properly and you consider, you see that for the area capture by this local alignments will not be from beginning of that sequence to the end of that sequence. So you try to look for area where there are good match. That's where it will do the calculation. So it will not start from the first amino acid and end of the amino acid. So depending on the close species that we are working with. So if the species is very far, maybe you are using human being, then you are using maybe toad. Okay, so we're able to see that the alignment, local alignment, we just go to area where there is good match between the two, and that is where it will do the calculation. So by that, we know that that area is somehow conserved between the two protein. Okay, somebody's okay. Definitely there will be differences. Okay, local alignment you have 91.61, then similarity 98.1. But for global you have 90.1, then 92.1. Then the number of gap you can see in global it will create more gap. But in local, since it's focusing on the area where they are somehow conserved, so no gap was discovered for local alignment. Thank you for that, Scholar Wale. So that is just what we can decipher from this particular analysis. So, but okay, thank you. So let me go back to the multiple sequence alignment, which is where we can construct our phylogenetic tree. If you are an MCB, this multiple sequence alignment is something that you must familiar yourself with. Okay, let's say, for example, you are working with ribosomal protein, maybe your 16S RNA from one microorganism. So you can get all the 16S ribosomal RNA from your organism, then come and do blast to get how they were similar with different types of organisms. Then from there, you do multiple sequence alignment, then you construct your phylogenetic tree. So that is what they do by the time they say they want to characterize a particular microorganism. They will sequence the 16S RNA or 16S rDNA. So either of the two, they will isolate it from the organism, then they will go and sequence it, get the amino acid sequence out. Then they will now do all this analysis to determine which organism does this one match. So if it doesn't match any existing organism in the database, so what they will need to do, okay, which one is the closest? So by that, they know that this organism that we have isolated is closest to this particular family. maybe it's a member of this particular family. So if the strain has not been identified before, they will give it a name. Okay, this is another strain, so, and so, as a result of that. So let's quickly go back to multiple sequence alignments now. Let me go back to my notes. Okay, on this note, to conduct multiple sequence alignments, we still use the tool from EBI. So just follow the link, ebi.ac/tool/MSA. Then we want to use the one of a cluster omega. We have the one of cluster W, but I think this particular one supersedes the one of cluster W. Okay, so just click on the link as shown on the screen, www.ebi.ac.uk/tools/MSA/cluster O. So I will click on the link now. Okay. Let me go back. And some have not copied that. So this is the link that we want to use to do our construction of multiple sequence alignments. www.ebi.ac.uk/tools/MSA/cluster O, CLUSTALO. Okay, let me click on it now. So I'm on the interface of cluster omega, is term cluster O. So it's for multiple sequence alignments that generate alignment between 3 or more sequences. And it can align up to 4,000 sequences. So can see as many sequences as you want to align and generate phylogenetic tree for, you can easily use this particular tool to align it. So since we are working with a protein, so we don't need to change this particular one. If you are working with RNA sequence or DNA sequence, you can easily change to the type of sequence that we are working with. But we are working with protein sequence, we still the same protein. So he said sequence in any format. So here you just have one box. So you have to paste, since we have 8 sequences in our MS Word. So just copy everything, all the 8 sequences at once, and come and paste it into this box, starting with that greater than sign. Okay, for everything, just copy everything that you have pasted on the MS Word, copy everything, and come and paste it into this search box. Let me wait for you to do that. So what are the format? Okay, let me see if it will bring it up. Let me go back. Okay, so while you are doing yours, I will try to use the example that I have on this interface so that I'll be able to explain the results to us. So just copy all your 8 sequences in your MS Word, paste it into this search box. Okay, let me see. Okay, leave it at the output format cluster W with character count. So the character count will try to count the number of amino acids at the position where they match. We see it in the result. Then you don't need the notification by email. The result will be out within a minute or 2. So let me use example sequence here. Okay, so that I'll be able to use it to explain for you. So once you have done that, just click submit. So I will submit the sequence, the sample sequence that I have there. Then you click your own and submit. So it takes you to this interface, tells you that, okay, your results job for this is still this. Okay, since I use just 3 sequences.
I've been able to see the sequence, everything.
Okay. Okay, you have this kind of a results page, right?
Yes, sir. Everything.
Okay, good. So let's wait for others to do that.
So fast.
Yes, it doesn't take time. So, but the more sequence that you want to align, let's say you want to align 100, then the time we take more time. So since we are just aligning just only 8. So let's wait for others to get to this particular result page. So once you are here, the results will be on this interface. Will be on this interface. Okay. It will be on this interface. It will show you the alignments. How all your protein, your own should be 8. I'm just using sample sequence here now. So how the 8 protein, how they are aligned. Then per each of the block, okay, the number of amino acids in this first block is 60. So the second one from 61 to 120. Then the last one from 121 to 142. So each block, the number of amino acids present in each block will be on this right-hand side. So that you know if you are looking for maybe amino acid 123, you know which block that you need to check. You know which block that you need to check. Okay. So if you want to color to see different amino acid, whether they belong to the same family or not, what you just need to click is to click on color. Once you click on color, it will try to color, click on color. You try to color the amino acid for you. So that easily you can see those ones that belongs, that are similar, or those ones that are identical based on the color. You can easily filter it out. Look at this second amino acid now, V. In the first organism, you have V. Then the third organism, you have X. You have X. So the reason why you don't have a gap in this part at this particular point is that valine and serine, they are aliphat, what's it called now? They still belong to the same class of hydrophobic, if I'm right. Yes, hydrophobic amino acid. That's why they can still substitute each other without creating any gap. But in your own results, there will be a section where you have gap. Yes, it's that one is sure. So you have a section where we have dash. That is what I mean by gap. You have dash. So that dash means that none of the amino acid over there align. None of the amino acid over there. So you have to create gap in order to make the alignment generate good score. So each color represents for different amino acids and how they can interchange each other. So underneath, you will see star, some semicolon, colon, while some just a single dot. Okay. So the one that has stars means that, okay, all the amino acids in that block, they are what? They are similar, they are the same. Look at that first one, MMM on my screen. But if you check your own screen, you will see all these star, column, dots, okay? The section
Hello.
where you have...
Hello, lecturer.
Sir.
Lecturer.
Okay, sir.
Dr. Fatuki.
Yes, sir.
I'm sorry. We want to make some arrangement. We will pause your lecture now.
Okay.
Please, we will allow so that others will hear. We will allow Dr. Hannah to come up because of the arrangement, you know, like Dr. Sally is supposed to come after now.
Yes,
but he has to leave for a meeting.
Okay.
Like he explained before. And Anna too, Anna will soon leave the house. So please, we will pause this. After Hannah has finished, we will continue from where we have stopped this one.
All right, because we are taking much time. All right.
So please, yes, we have spent about 2 hours. Close to going to 2 hours now. Please, all of us who are participating, please, let us note where we have stopped now. Multiple sequence alignment. Dr. Anna will come up now and take us another part of the bioinformatics lecture. After that, we are going to come back to Dr. Fatuki Please, just bear with her because she has to travel over there. It's still morning over there in her place, and she has something she has to go and do. Dr. Fatogi, thank you. Will be